We're getting into macromolecules. We're getting closer and closer to actually talking about the things that you thought you would talk about when you signed up for the course. Again, we will not get into cute, cuddly animals this semester, but we will get into cells and looking at things under a microscope and poking wet stuff. What we're looking at today is basic organic chemistry. Now, there is an entire course denoted organic chemistry. It's a 200-level chemistry class. If you go on to take it, it will probably be one of the hardest classes you ever take in your life. It makes this class look like an absolute joke. Organic chemistry is the science of studying carbon-containing molecules. Now, I'm going to give you a little bit of background on organic chemistry. You don't need to know this. Don't take any notes on this. I'll tell you when to start taking notes again. I mean, if you really want to, you can, but I'm not going to ask you stuff on this. Just some historical background. Now, it's called organic, and the term organic has been co-opted in so many different ways. But the reason it's called organic was because there's this theory, or this proposition called vitalism, that held that there are certain molecules in the body, certain things that the body makes, that cannot be made outside of the body. They require a vital life force to build. Now, Hippocrates and Galenius and Aventia, these were all early scientists and early philosophers who strongly believed this. Early medicine was based on the idea that there are some things your body can do that just can't happen outside of the body. So that's vitalism. This construct held true for the longest time until this German guy named Friedrich Wöhler came along. Now, Wöhler also held strongly into this vitalism construct, and he was a chemist. What he was doing was, in order to be a chemist, you have to go through a lot of schooling. You guys know that. You don't just like jump out of high school and you're a scientist. Right. The thing is, you need to go on for some additional schooling. And he did schooling as a graduate student, and he worked with a substance called urea. Urea is it's the urine. You know, what your body creates is urea. There are crystals in it. If you ever wanted to see urine crystallize, it does. You get nice little urine crystals. Your body tries very hard to get rid of that. He looked at this year after year under scopes and tried to figure out how the crystals were formed for somebody else. And he swore he would never look at it again. Later in his life, after looking under a microscope for hour upon hour during graduate school, he was trying to create this thing called ammonium cyanate, which is NH4OCN. He created this in the lab, looked at it under the scope, hoping to see ammonium cyanate crystals. But what he saw was that sort of recollection to his past. He saw urea, crystallized urea. Now, up until he did that experiment, everybody thought there are certain molecules like urea that cannot be made outside of the body. Well, now he can make it outside of the body. He made it in the lab. This opened up a whole new field called organic chemistry. Because, think about it, where did most of the medications come from for curing people 200 years ago? Plants, animals, nature. These organisms were creating these molecules with their vital life force. Suddenly now we can make it in a lab. We don't have to harvest a whole field to get some, a bottle of an extract. Now we can make it. This is what spawned the pharmaceutical industries. We're producing chemicals en masse that can interact with the body in the same way that the molecules produced by the body do. This was big news. Okay, now taking notes. This all happens because carbon has three really important properties. It can form up to 4 covalent bonds. It can bind to a lot of different functional groups, and it can have different forms associated with it. We're going to go through each of these, but it can form up to 4 covalent bonds. That's its max, yeah. It can form less, and they're stronger. It can bond to lots of functional groups, and we'll get into what those are. And it can have lots of different forms to it. Now, the reason carbon can form 4 covalent bonds is because it has 4 electrons in its valence shell. Remember, its atomic number is 6. That means how many electrons total does it have in a neutral atom? 8. Okay, let me say this again. Its atomic number is 6. So how many electrons does it have in total in an electrically neutral atom? 6. How many will fill the first shell? 2. How many then are on the next shell? 4. How many more does it need to be stable? 4 more, because you need a total of 8. All right, so it's got 4 possible places to bind. But it doesn't have to get all of those filled. You could have 4 single bonds, or a combination of single and triple bonds. And double bonds, too. Sorry, I didn't want to leave out doubles. So here we've got a single bond between 2 carbon atoms. Here's a double bond between 2 carbon atoms. And here's a triple bond between 2 carbon atoms. All of them they fulfill the rules. They make this stable. Each of these has different strengths associated with it and different amounts that it can rotate and turn. So it's got a lot of possible ways it can bind to things. Because of that, carbon can form linear structures. Linear means straight lines. Linear line. So lots of carbons stuck together. It can form these insane branch structures where carbon just sort of breaks off and goes all over the place. Or it can form rings. And rings are really indicative of organic chemistry. So carbon builds these rings up. Again, lots of different forms, lots of different functions. Carbon is very adaptable. Now, when it's bonding, oftentimes it's going to bond to hydrogen. Carbon and hydrogen have super similar electronegativity, which means, what are they doing with electrons? Sharing them equally. Very, very easily, leading to nonpolar molecules. How will this carbon and hydrogen molecule react with water? What would you term this in the way it reacts with water? So they have very, very similar electronegativity. They are sharing electrons evenly. It is nonpolar. It's hydrophobic. Water will be pushed away from it. There's nowhere for water to bind to it. Stupid hydrogen bonds. Functional groups are groups of atoms with characteristic chemical properties and features. And there's lots of different functional groups. There's like 20 different functional groups. Here you can see, here's a functional group down here, an amide group. Here's a nitro group, an amide group, a ketonic group, an ether grouping. There are lots of different groups. These are going to be repeated subunits. I believe I'm going to give you a whole chart. Yeah, there it is. So this is the functional group chart. These are the functional groups I'm going to want you to understand. So let me see if I can put it a different way with functional groups so you really understand what's going on. We've got the central carbon atom, right? It has 4 places that it can bond to things. We're good on that part, right? Everybody's so far so good. It can bond to any of these functional groups or other molecules. And if it does, it picks up the function they have. Methyl groups, hydroxyl. So they sort of attach, and they've given it some sort of new properties. Okay. Any of you guys have a mixer? Yeah. Okay. What kind of mixer? Anybody have one of those KitchenAid mixers? They're like super expensive. Yeah. Yeah. I've always wanted one, but I can't. And truthfully, I haven't actually wanted one. My wife has wanted one. But here's the thing. A mixer, that would be like the carbon atom. It doesn't do much on its own. You need the attachments for it. And you've got different attachments. You got that one attachment that's like a whisk. What do you use that for? To mix things. Well, mix things, beating things, right? You beat eggs with it. Yeah. You guys know what a whisk is? Yeah. Okay, sorry. This is a whisk. In my head. All right. You've got another one. They sort of look like little squares. They spin around really fast. You know what I'm talking about? You like a batter splatter? That's yeah, like you're making brownies or something. It's like a mix. It's a mixer. It's they're for mixing. What are those things called? A beater. Yes, that's what they're called. So you've got the whisk attachment that's for beating eggs. You've got a beater that's not actually for beating. The beater is for mixing, like brownies and stuff. Two distinct functional groups. You use one for one function. You'd use another. You attach it to that same central component. You got another function. And then you got that one that's sort of like all squiggly. Do you know what I'm talking about? Yeah, oh, it's a dough hook. Yeah. Yeah, no, there's another one, and nobody uses it. Yeah, it's curved. It's got these weird looks. It's got you can't beat an egg with that. Totally different function, but they still attach to the same large central grouping. That's the same way functional groups will interact with the carbon atom. If you don't like the baking analogy, my dad has decided that I'm a grown-up now. I know, right? And I need to do more work in the yard. So he had this idea a few years back. He got me this thing that's like a motor. And that's all it was. He's like, this motor's for you, and it's got a little handle on the end. And I was like, thanks. What's it for? And he's like, I'll show you next year. So the next year he got me an attachment for it that was a weed whacker. So now I've got a motor and a weed whacker attachment. I put it on, I've got a function. The weed whacker head will help me cut along the fence line. And I was like, thanks. More work. The next year, he got me a tiller attachment. So I can remove the weed whacker and attach the tiller. And now I can dig up my yard for reasons unknown. If I'm doing this, yeah, like I would do that though. Right, and then the year after that, he got me a hedge trimmer for it, so I could pop it off. He's so proud of himself. Another one has a saw blade to it. Yeah, so I've got all of these things with a central motor. That would be like the carbon. And then you got the functional groups, the extra attachments you put on that give it a new function. Carbon's awesome. So we've got these different functional groups, the methyl group, the hydroxyl group. Hydroxyl is pretty easy to remember, right? Hydroxyl, hydroxyl, hydrogen, oxygen. Amino, carboxyl, which is, I like carboxyl is one of my favorites. It's a COOH, C-O-O-H. It's cool. Aldehyde, a phosphate. How do you know it's phosphate? It's got a freaking P in the middle. Sulfhydryl, sulfur and hydrogen in a phenyl group. They will be on the test. But here's, I'm going to be super nice to you. You will not have to draw them.
So I have to label them?
Yeah, you're going to have to label it. No, you know what? I'm going to make it even easier. You're going to get matching on this. I'm going to give you 4 of them. You've got to figure out the name, match the name to the structure.
You give us the name.
Yeah, and I'm giving you the name, giving you the structure. You put what's what. Nope. No, it's one of these. No, nothing hard. Nothing hard. Pardon? This is included. 3. So we got these functional groups. Now, between the 4 possible ways that carbon combine and these functional groups, we can end up with lots and lots of different forms. Sometimes you can get 2 structures that have exactly the same molecular formula, but very, very different structures and characteristics. Those are called isomers. Iso means same. So isotope is the same number of protons with different numbers of neutrons. Isomers are the same structure. I'm sorry, the same molecular formula, but different structures. So if we look here, we've got 4 different types of acids. I'm sorry, 4. 3 types of acids. How many carbon are in the first one? 1, 2, 3, 4. How many oxygen? 1, 2, 3, 4, 5, 6. And hydrogen, 1, 2, 3, 4, 5, 6. So C4H6O6. Here we've got how many carbon? 1, 2, 3, 4. C4. H's 1, 2, 3, 4, 5, 6. H6. Oxygen 6. C4H6O6. Same exact molecular formula. And the final one, 4 carbon, 6 hydrogen, 6 oxygen. Each of these has the exact same formula, but they're distinctly different from each other. Here, you got mirror images. So what was this is now this. Thanks. I'm glad it helped. Here, they've gone from being on opposite sides to being on the same side. Those are termed isomers. Now, isomers matter because they have different forms, and thus, what do they have? Different functions. I want to tell you the story of thalidomide. Thalidomide, I know. Ooh, ready for a good story? Back in the 1950s and 60s. Back when the FDA was young and brand new. We didn't always have the FDA to protect us, by the way. There was like no regulation. Life was like happy for the drug makers. That's true. The FDA was formed, and they were all uppity and stuff like, we're not going to allow things to happen. Over in England, they didn't have that. There was a company that was producing a new type of anti-nausea agent called thalidomide. This was marketed to women who are pregnant because morning sickness is bad, and they don't want to puke all the time, as we just discussed about low pH and stomach acid. So they tested this, and they tested it on mice and rats, and they said, look, these mice and rats, they produce, it's fine for pregnant women. They're not getting, right, because they're rats. The rats were fine. They said the testing worked out. They put it out, and they started selling it like crazy. Now, thalidomide was an isomer of another anti-nausea agent that was totally fine, but it was cheaper to produce. But because it was a isomer, it had a slightly different structure to it, cheaper to make, different structure, different form, different function. Well, it did, in fact, reduce nausea. So then the company said, we want to go sell this in the States. Well, the FDA, they just came around during that time, and they said, no, you can't do that. You need to test this on higher primates first. And they said, well, we're in England. We can't do that. We're not allowed to test on them. We don't have, well, they had laws against it. Well, they said, well, here you're in America now, and you're going to do things our way. So they said, fine. So they contracted with the company to do primate testing. Now, by the time the primate testing finished, the primate testing showed the same thing that was happening in England. The higher level primates, when they gave birth, ended up giving birth to offspring with severe defects. The offspring ended up, they had effectively malformed limbs. Their hands were growing out of their arm, their hands were growing out of their shoulders. Their feet were way much closer to their hips. And because it was the 1960s and they decided to do this, they called them the flipper babies. I know, isn't that mean? But if you want, you could read about thalidomide and the flipper babies because, and not a generation, but for about 2 to 3 years, a lot of the kids born in England had these severe birth defects. But didn't affect us because the FDA said, yeah, no.
Did they die very early?
No, they're still alive. Like I was just watching a show. I was just watching a show on Netflix called Very British Problems, and there's a guy who has it on there as one of the people talking about the very British problems. It is. The great part is those of you with computers are all like, I want to see.
Some of them are still like
So we have two big kinds of isomers, structural isomers and stereoisomers. A structural isomer is one where they have the exact same molecular formula, but very, very different binding arrangements and spatial positions. This N-butane is very, very different from isobutane. They have entirely different structures. It's like it was pulled apart and put together in a totally different way. So the way I think about this is I think about Legos. All right, check this out. So we got a Lego car, right? It's got a form, it's got a function, it's got little wheels on it, it can drive. Whee! All of the pieces in this would be sort of equivalent to the pieces in these molecules. You could pull it apart and put it together in a different way. There we go. That goes there. I don't know. This piece can come off of here. It's just simple rearrangements. Put the wheels on a different place. Wheels here. Take that wheel too. There we go. And put that over there. And need that wheel too. Right. And now it's got a totally different form and function. Now it can fly. No, I'm not going to. It's like, whee! Entirely different bonding arrangements. Things have been moved around entirely different places, so it has a totally different form and function. So that's a structural isomer. Stereoisomers, on the other hand, have identical bonding relationships but different spatial positions. They go from being this to being this. There's the pivot, and that's all it is. You're pivoting on the bonds. Between D-glucose and L-glucose, the big difference is they're almost mirrors at some of these central points. So they stay in the same bonding relationships. There's still, right here, there's H to carbon to O to H. There's H to carbon to O to H. But it's flipped, but they're the exact same bonding relationships, just different spatial positions. Pardon? How's that going to affect it? What ends up happening is one of these is more useful for human consumption. The other one is useful for industrial processes. It actually does have an impact in the way you can process it. Yeah. So the way I can remember stereoisomers is I think about transformers. Now, you guys, I assume it's probably Michael Bay movie, which wasn't nearly as cool as the 80s cartoons, but I totally get it. And if you think Transformers, you might understand this, because the Transformers didn't break apart and come back together, except that one time, stupid Optimus Prime and a horrible. Anyways, it was dumb. Have you guys ever played with Transformers as kids, or like yesterday? No? Well, now's your opportunity. So, this is Starscream. It is. It's totally Starscream. So this is Starscream. Right now, he's in a plane form. But what? Do it quick. It took like an engineering degree to get this figured out last time. Yeah, it's got an insane number of steps. Come on, break your legs. There we go. So I just start twisting. Now I'm not breaking anything off. I'm just moving it around. And as you twist and turn, I don't understand why Starscream has high heels. Oh, okay. But all I'm doing is pivoting bonds. I'm not breaking any bonds. I'm not ripping anything off. But in doing so, you've gone from a plane to a spindly-looking robot. But the idea is all you do is twist the bonds. If I broke it off and replaced it, I'd have broken my toy. So totally different bonding relationships. Yeah. Now, I want to give props to a former student of mine named Laura Haley, I believe her name was, who came up with this idea because I brought this up and was like, Starscream. And she's like, actually, if you think about it, it's the stereoisomer. So a better example would have been Bumblebee. Now, why would Bumblebee have been a better example? That's right, because he talks out of his stereo. But the rest of you guys don't care, and that's cool too, I guess. I thought that was really cool. So we got stereoisomers that pivot on their bonds, and structural isomers that are going to be sort of pulled apart and put together in entirely different arrangements. Oh, tricky.
There's a lot though.
So, 3 big properties for carbon. It has 4 covalent bonds. It can bond to lots of different functional groups. And these carbon-containing molecules can have many different forms. Now, so we've got this idea of building molecules. We can have small molecules come together to form larger molecules. And they do that by linking together. And in doing so, they can have entirely new emergent properties. This is the student body at the University of Virginia. A few years ago, the Board of Governors at the University of Virginia decided to get rid of their president, President Sullivan, as you can see in the signs. And so one of the students, or a few of the students, were very concerned. And they went to the Board of Regents, or the Board of Governors, and said, we really like President Sullivan. We don't want her to leave. Now, the Board of Governors said the same thing they would say to you guys if you went to them. We really appreciate your input. Thank you for bringing this to our attention, and we'll look into it. Which is political, right? So what did the students do? Well, they didn't give up. They just started getting more and more students together. Well, a small group couldn't do much. But when you get thousands and thousands of them out there, suddenly the Board of Governors said, you know, maybe we made a mistake. It wasn't, you know, it was actually that guy over there. Oh, he's a jerk. He's leaving. We really like President Sullivan and want her to stay with a raise. So it can work. You just band together. We have to get these small molecules, these individual pieces called monomers, very small molecules, to link together. And they're going to come together and form polymers. So monomers, mono meaning one, individual subunit, they're going to bind together to form polymers. How are they going to bind together? What kind of reaction are they going to use to get stuck together? A chemical reaction, thanks. No, in real life, how would you describe said chemical reaction? What kind of chemical reaction is it? When you're taking 2 molecules and bringing them together. Wow. It's not hydrolysis, it's the other one. Condensation synthesis, they're condensing. So monomers and polymers can come together. Monomers can come together using condensation reactions to form a larger structure. And that larger structure could have entirely new properties. Right. Thank you guys for understanding. This is Voltron. Most people are like, it's a Zord. Or it was a Megazord. It's like, it's not a Megazord. You're wrong. From Power Rangers, if you were totally lost on that one. It does. So here we've got 5 individual subunits. Lion, 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 lion. They come together, and when they come together, they form a much larger structure that has cool new properties. This one can pull out a sword. As actually, have you guys ever seen, what was it? It was Mighty Morphin Power Rangers, wasn't it? You guys remember that show? You guys know?
Chances are they've seen a Power Ranger show.
It looks mildly similar to the concept of like the Power Rangers Dino Wars.
Right.
Where like they all had a different dinosaur, but then you can tell because one had like a Triceratops hand, the other had like a.
It's all about bringing these different things together. Now, if you recall any of these shows, they all had the exact same premise. We're going to start fighting these bad guys totally separately. What happened every time they did that? They lost. They lost badly every single time. And then what happened? Then they said, let's fuse together. And we have new properties. So it's these individual monomers coming together to form a polymer. Teamwork and friendship is important. All right, so we're going to take these monomers, build these polymers using condensation reactions, otherwise known as dehydration reactions. Now here's the deal. Whenever you have a condensation reaction, you have to build, and building requires energy. The energy that you're using gets stored in the bonds. So you can build macromolecules to store energy for later, so you don't have to use it all right now. When you need it, you can release the energy, and you release energy using hydrolysis reactions. Here we have a bigger molecule, sucrose, and you cut it using water, and it breaks apart, and when it breaks apart, it releases energy. So condensation reactions are going to store energy through building. Hydrolysis reactions are going to release energy through breaking bonds. Because in the end, energy...
There we go. Organic molecules are those that are characterized by carbon, especially carbon rings. So when you think a ring, think carbon. You could also think nitrogen sometimes, but for this course, think carbon. And carbon is very important to organic chemistry. Carbon is a very important molecule because it's got a few basic properties to it. One, it's got 4 places that can bond with other molecules. It's got 4 valence electrons. That means it can bond with lots of other functional groups, and it can bond with many different, in many different forms, so it can create different isomers. When we're working with organic chemistry, specifically working with macromolecules, we're going to take lots of little small molecules called monomers and string them together. These are repeated units over and over and over again. And we can put them together using what are known as condensation reactions or dehydration synthesis. This requires energy to build a bond and form a polymer, many units. Energy gets stored in those bonds, or it can be stored in those bonds. To release that energy, or to break these bonds, you may undergo what's known as the hydrolysis reaction. So there's a lot going on there. Here are the content review questions to really focus your studies on the important topics in this mini lecture. They're all important, otherwise I wouldn't be telling it to you, but you could really focus in using these content review questions. And stay tuned for the next lecture in this series, which is about the 4 types of macromolecules, which we covered 2 of them. The 2 we're going to be covering are carbohydrates and lipids, and in the lecture after that, we'll talk about nucleic acids and proteins.